everybody. Great to see you all here today. Thank you for coming back to Northeastern. Welcome back to all of you who are alumni especially. Are there any engineers that are here? Oh, wow. Okay, many more than I was expecting. All right.
You have to rewrite your speech.
I know. Yeah. Well, that's okay. We can adapt and improvise. So I'm going to talk to you today about some work that I've been doing and a few of my colleagues have been doing for a number of years now, thinking about new urban regions, and in particular thinking about a new generation of solutions for complex urban regions. We're going to talk today about ideas of resilience, bouncing back quickly after extreme events, ideas about sustainability, thinking if we can work with our built environment to greatly reduce the amount of energy that we use, the amount of waste that we produce, and so on. So we've been developing a number of solutions over the years to these sorts of issues, and look forward to the discussions today. The story starts today in Kobe, Japan, a great city in Japan, a beautiful city and a really important port city in Japan historically. At the risk of condensing a few centuries of history into a sentence or two, Kobe was one of two cities that were open to the external world during the 200 years or so that Japan as an empire closed itself off to the external world. So it was a rare cosmopolitan city in Japan for a couple of hundred years until the country opened up in the 1800s. And if you go there, there's a lot of international architecture as a result of this. In fact, you can go visit a house from Frank Lloyd Wright. That was designed by Frank Lloyd Wright. Kobe is part of a triumvirate of cities in central Japan, along with Osaka and Kyoto, that really form an important economic hub. When I go there, which I do periodically, I stay at the Portopia Hotel, and this is the view from the breakfast room up on the top, overlooking their renowned port facility. And I would venture to say that many people in this country haven't really heard about Kobe, Japan. Has anybody here been to Kobe, Japan? There you go. A couple of you, great. Really, few of us had heard about it, perhaps at least until they had a significant earthquake, which had occurred in January 1995. And it was on the high side of a moderate earthquake, magnitude 6.7 by the scales we usually use. And the crane facilities in their ports collapsed. There were gas main explosions, so fire raged throughout the city. Japan is perhaps premier in earthquake engineering, and yet they had modern structures like this one that collapsed. Their transportation infrastructure was devastated in this earthquake. The Akashi Kaiko Bridge, still the longest suspension bridge in the world, was under construction at the time, and you could see there's two main pylons. One of them moved about 1 meter relative to the other, and they had to redesign the bridge just to be able to finish it. But what happened to the port facility is particularly significant for a city like this because the ports provide such an economic engine for the entire country, and certainly for that part of the country. If you go to Kobe today, which I encourage you to do, you could go to their Kobe Earthquake Memorial Museum, a pretty rare opportunity. And they have docents there who, in their broken English and my very broken Japanese, we were able to have a conversation and piece together their stories that they told about the days and the weeks and in fact the years that it took them to recover and their families to recover from an earthquake that's on the high side of a moderate earthquake. And this repeats itself. Just thinking about earthquakes for a moment. 2008, some of you might remember the major earthquake that caused a lot of discussions about corruption in the construction industry in China. 70,000 people dead. In Pakistan, 2005, whole villages completely leveled, totally gone. 1976, when I was young, I don't remember this one, but I've read about it. 255,000 people dead. I mean, that's more deaths than you have in all the other natural disasters you could think of combined. And what do we do with a city like Istanbul? For me personally, my favorite city in the world. It's a spectacular place, really interesting connection between Europe and Asia. And this shows an image of the North Anatolian Fault cutting across northern Turkey. And if you look at the years here, these are the years of some of their significant earthquakes. And as you start on the east of Turkey and go to the west, 1939, 1942, 1943, 1951, 1957, 1967, and way on the left is Istanbul in the yellow dot. So the North Anatolian Fault is unzipping right towards Istanbul. The last one, 1992 in Izmit, was a significant event. This shows the energy that's being released by these earthquakes every few years as the fault opens up. You know, we talk in this country after we have major floods, like the Mississippi River in 1993, some of you might remember that. Certainly what happened in Hurricane Harvey. Should we move people out of the floodplains? And it's a difficult policy question. But what do we do with a country like Japan? The entire place is a high seismic zone. You can't move an entire country. And of course, most recently, they felt it in the extreme, 2011. This was a significant earthquake, magnitude 9.0, that caused a huge tsunami that, of course, destroyed portions of this nuclear power plant that caused radiation issues that they're still grappling with now. And these types of issues don't just happen on the other side of the world. I don't know how many of you remember the 1994 Northridge, California earthquake in Southern California. Were any of you in California at the time that this earthquake happened? All East Coasters here, huh? So, relatively small number of deaths, although any death is something we try to avoid. Same with injuries. But $30+ billion at the time, 1994, a year before the Kobe earthquake, costliest natural disaster in the country's history. Yet a lot of us probably haven't even heard about it or thought about it. And it had about 1,600 timber structures condemned, 300 concrete structures, only 10 steel structures condemned. How could this be the costliest natural disaster in history? Well, this gives a window into what we're talking about when we talk about resilient engineering, bouncing back quickly after an extreme event. This is a newspaper article from the LA Times, and it shows a typical steel building structure, modern structure at the time. This is, if you have a building just like this, you would have steel beams framing into steel columns holding up the structure and resisting the earthquake as it shakes back and forth. And what they found about a month after, as they were repairing some non-structural damage on a building, they took off the drywall and they saw that there was a fracture between the girder, the beam, and the column. Down at the bottom flange, you could see on the lower left in the zoom in, that black line is a fracture, meaning there's an unexpected crack there. And so they started taking drywall off from a number of steel buildings, and they found more and more of these fractures. And so they ended up having to inspect the city, and in fact they ended up shutting down steel construction in the Los Angeles region for a couple of years after the earthquake, while they tried to figure out what happened and how to prevent it from happening again. That will decimate an economy. And that's what happened after the Northridge earthquake. Oops. By the way, in the map here you could see the red is near the epicenter, so that's a bit north of Malibu, and Los Angeles is down to the southeast there. This is a zoom in for those of you who are engineering enthusiasts of the fracture. This is a steel girder in a building framing into a steel column, and you could see it ripped out a whole divot. The amount of energy it takes to do that to structural steel is huge. So this is a typical example. This is a corporate headquarters from Borax Corporation. And they had a steel building structure that was 4 stories tall. It had several bays of steel beams and steel columns, and the nomenclature that you see in the figure, so these are the steel frames that are holding it up from an earthquake. That's where all the fractures happen, wherever the nomenclature is. Now this was a building that was less than a year old at the time, and it was designed by a perfectly fine engineer, and it met the building code. And corporation was self-insured. And so I think they almost went out of business because their corporate headquarters all of a sudden had huge damage in it that they deemed to be unexpected. In this country, we hadn't really been talking for years about what we call the disproportionate collapse. Disproportionate collapse is when you have a structural collapse that seems to be totally out of whack with the magnitude of the load. They've been talking about it in the UK after the Ronan Point disaster in 1968, where a gas main exploded down in the basement and a quarter of the building, or a good portion of the building that you see here, collapsed. And structural engineers started thinking, that doesn't seem right. We didn't talk about disproportionate collapse much in this country until 9/11. Now the loads here, a lot of structural engineers would deem to be extremely large in this incredible tragedy. And the fire that happened is really what caused the collapses, I think, in many people's opinions. But certainly to have something like this happen gives a wake-up call to how we're thinking about our designs. And then you could start thinking about what we want to talk about today, which is whole urban regions, not just individual structures. And so you think about Hurricane Katrina, which I'm sure you all remember in New Orleans. And a major part of the disaster that happened there was due, in my opinion, to a disproportionate collapse. A portion of the levee system, designed properly by the U.S. Army Corps, in many people's opinions, collapsed. And that caused flooding throughout the region that greatly increased the tragedy and the economic losses. So to be resilient, these are intertwined issues that we haven't really been thinking about. Kobe was the 6th largest port in the world at the time of the earthquake. And in 30 seconds, it was wiped off the face of the earth economically, and it hasn't recovered since. Right at a time when shipping was going up exponentially, shipping traffic. In the US, you can think about our high seismic zones, shown in red here. Certainly the West Coast. Been a lot of press in recent years about what's going on in Seattle and that region and whether we understand the potential magnitude of the earthquake. For years when I was at Illinois, I worked in the Mid-America Earthquake Center studying what might happen in Memphis, Tennessee, or in St. Louis, Missouri, due to a deep buried fault by our limited understanding. Charleston, South Carolina, indeed north of us up in Quebec. So what does it mean to be resilient, to bounce back quickly after extreme events? How can engineers start baking resilience into the design process? Because right now, we don't. We think about things like collapse prevention, but we don't think about how to bounce back quickly. And that's what I'd like to change. And the disasters that are happening seem to be coming on with increasing regularity. Superstorm Sandy, Hurricane Harvey, Hurricane Maria. Sam Slyman is the Director of Capital Projects and Environmental Affairs at Massport, Logan Airport. He's a graduate of our program, great supporter of our program and a partner in our research and teaching. And he's thinking about resilience because he knows that Massport is at sea level. And he is trying to think proactively about what it means to bounce back quickly after extreme events. Simultaneously with this, we're thinking about sustainability. So construction and use of buildings consumes about 40% of all energy use, about 40% of all material resource consumption, about 40% of all waste, creates about 40% of all waste, and creates about 40% of all greenhouse gases. And you can see transportation and industrial facilities account for the other 30%. These are rough numbers, plus or minus. But it gives you an idea that construction and use of buildings consumes a lot. And so we'll be thinking about sustainability and resilience and new solutions here in this context, at the same time acknowledging a broader set of questions from some key disruptions that I think all sense are happening. Technology revolution and globalization are two good ways to summarize it. These are from Glenn Bell, chairman and former CEO of Simpson, Gumpertz & Hager right here in town. who I'm able to talk to and brainstorm on things like this quite a bit. And he put together the next few slides of some of the major trends that he's seeing that civil engineers need to start thinking about. Population explosion, we've been talking about for decades, poverty and hunger, health and pollution, scarce resources, climate change, security. If you start to put all these together, we've been working with the faculty at Northeastern and the students to try to pull us up a bit from what I'll call component engineering, designing an individual project, an individual building, an individual environmental remediation, and thinking much more systemically about what's happening to create new solutions that we think can be better. So let's look at a few of these. The way in which we design buildings right now, for example, for earthquakes, and this is by code. You could summarize it by saying for a light earthquake, we design it so that there's no significant damage in the structure, you can have immediate occupancy. For a moderate earthquake, we design it so that it's probably going to be damaged in the primary structural system, but it should be repairable. In many structural engineers' opinion, that in fact is what happened in the moderate earthquake of the Northridge earthquake, the moderate magnitude of the Northridge earthquake. And so there's debate there. Should that much damage have happened for that earthquake or not? But we're in that gray zone. And then for a large earthquake, we design for collapse prevention. We can't design for an infinite magnitude, but we design for pretty large earthquakes to try to make sure it doesn't collapse. But we don't design them not to be significantly damaged, so damaged that they might be condemned. And so there's a trade-off there. How often is the earthquake going to happen? How often is the hurricane going to happen? How often is the storm surge going to happen? How often is the tsunami going to happen? How often is a major snow load going to happen? So I think we can do better. And I work a lot with the National Building Codes and steel structures, and we've been trying to get some of these ideas. A lot of researchers around the country are starting to think about some of these ideas as well. Here's one example. You could use the same construction materials that we do now and re-proportion where the elements are. This is a structural system I worked on with some colleagues at Stanford University, including Greg Deerline, who we developed what we call a controlled rocking system. And so it starts with, for example, in this case, 2 steel brace frames, just like you would have normally in a building. But we allow them to rock free of the foundation in a trough. And then the gold elements are, we call them replaceable energy dissipating fuses, like the old fuses in your basement. And these are standard steel plates with diamond-shaped cutouts. And by cutting out those diamond shapes, they can shear plus or minus 30–40% of their dimension without failing. And through that, they absorb the energy from the earthquake. And then the green lines, vertical, are post-tensioning that snaps the building back to vertical. After the earthquake, you pop out the old fuse, put in the new one, ready to go again. So we tested this in a variety of different ways to see if the system worked. And the culminating test was at E-Defense, the largest shake table in the known universe. It's outside of Kobe, Japan, and it was Japan's research answer to what happened in the Kobe earthquake. They built this massive shake table. And this shows a schematic. In this particular configuration, we've got one brace frame surrounded by these gray elements, which I'll talk about in a moment. So the specimen here is a single frame, and the white post running down at the bottom in the center, as you sway back and forth, is going to go up and down, and it shears the fuse that's at its bottom. You can see it in the blue on the left. And then surrounding that fuse are vertical post tensioning. So it's a single frame configuration of what I was showing you before, but the same idea. Here's the shake table. You can see a little person there. This is at 2/3 scale, so the specimen's about 30 feet high, 3 stories. And the big gray things are inertial masses. On each floor, they're going to slide back and forth relative to one another. And they throw all that inertial mass while the shake table shakes with the earthquake into the specimen, down into the fuse, which is, along with the post-tensioning, the only thing that's holding this up from failing. You can see the shake table, the troughs around it. On the right, those green things are the big actuators. So this shakes in real time just like an earthquake. 6 degrees of freedom, we call it. It can do 3 translations, 3 rotations. It's very disarming. and a powerful facility. So hopefully this will work. This is a video. Yeah. And what you're seeing on the lower right is an overview of the specimen. It's hard to, the specimen. The specimen is actually the gold frame. You can see a little bit of it towards the bottom. Those are the three levels. You'll see them shearing, sliding relative to each other. On the top are the two corners going up and down as it rocks back and forth. Those are a zoom in. And on the left is the fuse, on the bottom left. And you can see the fuse in action there. This was an earthquake that was about twice as large as the Northridge earthquake. And about as large as our Japanese friends let us put onto the table before they said, okay, don't break our table. Our Japanese colleagues love the system. They helped us a lot with this. Great example of some interdisciplinary and international research. So it takes years to get these into the building codes in our litigious society. But you can have pioneering engineers who are early adopters and start to use this, and they just have to talk to the building official in their region to get it approved. And so that's happened now. For example, David Marr used this system with a two-story brace frame, and the post-tensioning is looping underneath the foundation there. And the fuses are these deformable angles down at the base. So this whole system, this frame will rock back and forth like you see in the animation here. And then here, instead of the butterfly fuses, as we call them, they have these deformable angles that can be replaced after the earthquake. You can see some post-tensioning in the column. And then there's some other innovations, like some slotted connections here to enable the rocking, pin connection up at the top to enable the rocking. And overall, the system works. The Orinda City government building is using this system. University of Southern California School of Cinematic Arts is using the system. This is, instead of steel brace frames, they're using precast walls. And so long as you have a stiff spine, like a brace frame or a precast wall, it's all about the same. And you connect them together with these fuses, and in our opinion, it should work quite well. And make these structures much more damage-free after a huge event. And you know, buildings get condemned not because the non-structural stuff gets damaged, it's because the structure gets damaged. The David and Lucille Packard Foundation headquarters in Los Altos, California uses the system pretty much verbatim to what I showed you from the e-defense test. And David Marr is thinking about even taller buildings and reconfiguring this system in a variety of ways. Then we're taking this idea to other types of structures, maybe the power infrastructure, maybe the pipeline infrastructure. This is for bridges and some tests we did at the University of Illinois. These are looking at bearings that are right underneath the girder, sitting on top of the superstructure of a bridge, like a standard off-ramp. The bearings are there to allow for some temperature control and temperature variation. We're seeing if they can work in a big earthquake in mid-America, because those bridges aren't necessarily built for earthquakes right now. And so we showed that it can actually act as a fuse and isolate the superstructure to help protect that structure. Andy Myers and I here at Northeastern are trying to make Massachusetts premier in offshore wind. And if you happen to talk more about that, there's some interesting things going on. And we'd like to help make the U.S. premier in offshore wind. There's enough wind energy off the East Coast to power the entire country. Now, it's hard to get it all the way across the country, but it speaks to the size of the resource. And some of what we're doing is looking at new designs for offshore wind towers, using, for example, fuses, so that a hurricane doesn't take out the entire power plant. I have an ongoing project now from the steel industry and the National Science Foundation to look at three-dimensional behavior of buildings during earthquakes. And in particular, if you have an irregular building, it's going to sort of rock and twist all over the place. So we'd like to use that motion to engage new types of fuses to dissipate the energy. Similarly, we look at new materials. We've been looking at steel foam. You can inject inert gas into steel during the steel-making process when it's molten and create foams that have a range of properties from relatively soft metals like aluminum all the way up to structural steel, depending on how many voids you've got. So it's a whole new range of materials that we can use for construction. And we've started doing some basic mechanistic testing on that to see how these would work out. Now, amazingly, for decades, we've been designing structures to try to prevent them from collapsing. But none of us actually know how to simulate collapse all the way to the ground using a computer. So we've been working on that here as well. And you can see an example of that here, so that we start modeling and simulating this directly as well as designing for it. We've also been doing a lot in sustainability, trying to develop new structural systems that use a lot less energy during construction. And one example that we've tested right here in the stress laboratory is we call Design for Deconstruction. And it was developed by Mark Webster at Simpson Gumpertz and Hajjar, and he and I have been working on this together for some years. And in this case, we're looking at a standard steel building that normally has a concrete floor slab. That's poured monolithically and attached with what we call shear connectors to the steel beam. It's not deconstructible at all. It's monolithic. And instead what we're doing here is we're creating a floor plan like you see on the right that consists of precast concrete planks that sit on top of the steel beams and are attached to it with clamps. The clamps in yellow there are relatively new products, and they can transfer a lot of force. So it's a new idea, one that the steel industry's not used to. I'll have to spend a number of years talking to them to see if we're ready for something like this. But if you do that, what it means is, in the context of bolted construction, for example, you can take the whole building apart at the end. You can stockpile these planks in steel supply centers in different shapes and sizes, and you could reuse them in future buildings. So right now, if you look at how our construction materials are dealt with, you can see on the right, 93% of steel is recycled right now in the US and around the world. Construction steel, structural steel, which is great. Recycling is great. And but it still takes a lot of energy. You've got to melt the whole thing down again. We'd like to increase that 6% on reuse to be the 93% perhaps, because we think we can reuse these so long as the building hadn't been subjected to an extreme event. You can see timber, which is starting to get really popular now, 60% of it goes to the landfill. And concrete, about 75% of it is downcycled, not really usable for construction again. So these are things that I hope we can improve on. So you're here at the Costas Institute, and I'd be happy to take anybody you'd like on a tour of the stress laboratory after this event. And the stress lab's down on the first floor. Its key feature is it has 416 holes that you could apply 200,000 pounds of force to pulling up on the floor. It's called a strong floor. And by doing that, we can tie structures down, and then we use these big hydraulic actuators to test them all the way to failure. This is how we determine if new structural systems can work out in the field. And so we did that with Design for Deconstruction. These show a couple of the test setups. It's very flexible. On the right, we're going to test a composite beam. And those black items are actuators that push down with the hydraulic force to test a failure. And so here's a couple photographs of one of our specimens. So there's on the lower left, you can see the beam, it's deformed. You can see those concrete planks deformed. This is what it would be like under huge gravity loads, for example. And on the right, you're looking at the underside, so you can see the whole thing deformed and curved. The system worked quite well even under these huge loads, and you can see the clamps there in silver clamping into the top flange of the beam. So that's an example of a new type of system we're developing. My colleague Matt Eckelman is an environmental engineer and an expert in what we call Lifecycle Assessment. So looking at the flow of energy use, looking at the flow of energy and materials through civil engineering processes. And so he's been helping me determine, do you have to reuse these once? Do you have to reuse them twice? How many times before the real benefits kick in? And we're finding that even one use is enough to have some real environmental benefits. And this frames into a bigger world that I think you're going to start to see increasingly, which is modular construction. Sort of a type of construction that a lot of people don't think that highly of because of the way it's been used in the past. But I think you can design first-rate buildings from it, and we can greatly cut down on our energy use because it's a lot more efficient to fabricate things in a shop, in a plant, than it is out in the field. And so I think the quote here is pretty relevant. And so we're trying to help rethink, and really it's a culture shift. Thinking about sustainability in our lives is a culture shift. And so that's what we're talking about here. The last thing I want to talk to you about is the use of robotics in civil engineering and some of the work I've been doing on this. I've been working with Carnegie Mellon, the Robotics Institute, and also here with Tashka Padir and some of the other robotics professors. We've done a lot of hiring in the area of robotics and electrical engineering here and some of the other disciplines. And what we're talking about here is using unmanned aerial vehicles to fly autonomously around structures in order to help with inspection. And this can be for routine inspection, such as major pieces of infrastructure. Just as an example, I have been talking to the engineer of the Golden Gate Bridge, who has to inspect the bridge 365 days a year, because basically they spend several weeks building scaffolding on one portion of the bridge, then they spend a few hours or a couple of days inspecting that region, then they have to take it all down, move down 30 feet, and rebuild it. And they're doing this constantly. And so he was very interested in this technology. And this could be labor intensive, dangerous, subjective, difficult to monitor over time. Now, we don't want to replace inspectors. We want to really provide them some tools to augment. And I started getting into this after investigating a small collapsed bridge in Illinois that you see on the lower left there. And sort of combining that with some other things I saw in the world of lasers. We take lasers and cameras and mount them on these UAVs. This is a railroad bridge that we scanned in Pennsylvania. You can see the UAV there, the copter. This is autonomous. It's not a drone. It's not being piloted. We give it a bounding box around the structure, and then my electrical engineering friends have taught it to go look at every nook and cranny. And through that, it maps out a complete three-dimensional geometry of the structure. And then my part as a structural engineer is to automatically develop a three-dimensional model, use that to create analysis models so we can predict behavior, and then also automatically detect damage. So you can see the type of result that we get here. So we did this on the Bowker Overpass. Right here, this is the on-ramp to Storrow Drive East over at Charlesgate, near Kenmore Square. One of the great things about doing work on damage detection in Boston is we have a lot of damage. No lack of resources there. So there's a couple of off-ramps that we did some scans on here. And these are the results of some of the laser scans. These are sort of zoom outs. And then from there, we're able to do things like create these complete 3D models automatically and mesh them down to little, we call them finite elements, that we can then use for structural analysis to predict stresses and strains and displacements in the structure due to various loads. And also automatically detect damage. So these show examples of concrete spalling that we detected automatically. Section loss due to corrosion, local buckling of the steel. We could do bent members, we could do out of alignment, etc. And we picked those bridges, in fact, because we could also access them by a ladder, get up there and measure the damage with a micrometer, so we were able to validate the results. And my colleague Mark Patterson, who has a joint appointment in our department in Marine and Environmental Science, is one of the world experts on underwater robots. So we're doing climbing robots, crawling robots, flying robots, underwater robots, submarines. And as you may know, our president just put out a new book called Robot Proof. And I encourage you to take a look at it. It's a great academic thinker. And we're thinking about how do we educate our students in a world driven by technology revolution, globalization. Mixing, in his opinion, and I think I would agree with him, deep understanding of the humanities with understanding of technology and engineering, at least for our engineering students. A couple of my colleagues out there are working in something called topology optimization, a whole new mindset for designing structures. This is from Bill Baker at Skidmore, Owings & Merrill. And instead of using the standard vertical columns and horizontal beams in a building, they start with a mass. And they use computer optimization to discern what the best form is to meet an objective. For example, minimize the horizontal drift due to a wind load. And you start to develop shapes like you see in the middle here that look much more organic than the structural shapes that we use now. And so Bill Baker has started developing structural systems that look like this, with mega braces on the outside. Now, that's a very natural and organic form. Would love to say that it's brand new, although I have to think that Leonardo da Vinci kind of figured this out a long time ago. But I raised this just to finish off here because I've started to think about topology optimization of whole regions. What we're talking about here is trying to build in resilience, build in sustainability for our individual projects, and then thinking about that, how that intertwines so that we can start to have a new type of urban planning in our regions, to make the whole region more resilient, make the whole region more sustainable. That's what we're doing in civil and environmental engineering at Northeastern. Thanks a lot, folks. Appreciate it.